could be the able to transform your change of area, wasn't that?
Good evening, everyone. Good evening. It's been a long weekend. I'm starting this off really well.
Very good,
yeah. Good morning, everybody. I'm really excited to welcome Sean Healy to come and talk to us. I've been wanting to have him come speak about his work for a long time, so it's great to have you here. Quick bio, like we do in these things. He's got a physics degree from the University of Leeds, from a very long time ago. He actually has a PhD in X-ray laser physics from the University of York. But then in 1996, he went to the Met Office and talked to work for John Eyre, who had this crazy idea that you could use the global positioning system for meteorology, and obviously nothing came of that. That was 2 years later he met me, which makes me feel very old, that was 20 years ago. 2003 he went to his present job at ECMWF, and now he's well known as one of the leaders in GPSRO assimilation and NWP in the world. So that's enough of that introduction, and Sean, take it away please.
Thank you. Is it okay if I sit? Do people normally sit for this? And I can
you can do whatever you like. Feel comfortable.
Okay. I'm happy to sit, so I've got...
Well, with the sit, at least, if there's anybody phoned in, they can see your cursor this way.
Okay, so, yeah, thank you for the introduction. It's a real pleasure to be here. I'm going to try and go through how we use the GPSRO data at ECMWF. The purpose is that if I can do this reasonably clearly, we can then start talking about how we use it differently here and ECMWF, and maybe in the future we can come up with some collaborations and comparisons about the approach we're doing. I should say that most of my work is funded by the EUMETSAT ROM-SAF. That's in terms of the forward operator development in particular. And I'd also like to acknowledge that a lot of the results that I'm showing have been produced by other people, in particular Steve English, Alan Gear, Niels Ballman, Heather Lawrence, Jackie Bill, Chris Burrows, and Adrian Simmons. So, this is the outline. I've split the talk into two bits, but actually I'll spend most of my time on the NWP bit. I'm going to go through the processing of RO data, and then how we assimilate the data, and in particular how the assimilation approach has evolved since 2006 when we were in operation for the first time. I want to stress that these are not all my ideas. I've kind of taken best practice from elsewhere, so you'll see cases where NCEP did certain thing that later I implemented because I thought it was a good idea, and so on. Then I'll just show some recent results demonstrating the current impact in the ECMWF system, and how that compares with different observing systems. So those are the experiments that have been done by Niels Ballman and his group. I just then move on briefly. I don't know. Okay, I've not done anything there. Briefly.
What's supposed to happen?
Doesn't matter. Doesn't matter. As long as I don't see rubbish coming. Oh, he's gone. I'll just show you some results that show how important RO is in terms of the climate reanalyses, and also show you what I call the temperature null space. And this is it's quite an interesting feature. It's a certain pattern of RO temperature perturbation that it really struggles to see, and then I'll summarise. I'm clicking that. Oh, that's thank you. Okay. So we'll go straight into the GPS RO geometry, which I'm sure many of you are familiar with. The technique really comes from planetary science in the 1960s, but it was only really available to Earth observation in the mid-90s. Essentially what we're looking at is to see how a radio signal that's from the GPS satellite, as it propagates through the ionosphere and the neutral atmosphere, the refractive index gradients in the atmosphere and ionosphere lead to the ray path being bent, and what we look at, or what we're trying to characterise, is how this bending alpha as a function of a vertical coordinate that we call the impact parameter A, and how that varies as we start to slice progressively lower through the atmosphere. This particular example is a setting occultation, but we also have rising occultation. The impact parameter A, people usually just think of it in terms of a geometrical parameter. You can see it is the straight line path that the path would, sorry, it's the height or the radius value that the straight line path would have had in the absence of any bending. But if you want to give a more physical interpretation, it's kind of analogous to the angular momentum of the particle. So you'll see, you can see similar pictures to this in, say, classical mechanics books by looking at how an object is deflected by a gravitational field, or a particle is, a charged particle is deflected by a nucleus and so on. Essentially, it's the same problem. So you've got your bending angle as function in that parameter is the key thing here. Some basic characteristics of the RO technique. It has very good vertical resolution, depending on how you define it. In the lower troposphere, it can be down to 100 meters, a bit broader higher up to 1 kilometers. But you have to bear in mind that it is obviously an average over a limb. It's a horizontal average. And if you look at this previous plot, you say this is the distance of closest approach here. Around about 70% of bending will occur over about a 450 kilometre section of the ray path. So it's got a very broad horizontal weighting function. And if you assume to first order that the refractivity or the refractive index falls exponentially with height, you can show that a refractivity, an exponential decay with height, implies a Gaussian shape in the horizontal. We usually say it's got an all-weather capability, it's not affected by cloud and rain, and some basic numbers that's worth knowing, because you get that from the pictures. The bending at the surface, or close to the surface, is typically 1 or 2 degrees, and the bending falls exponentially with height, approximately with a density scale height. And we tend to get observations, bending angle observations, that go all the way up to 60 kilometres. If you look at the duration of an observation, it takes around about 2 minutes to get from 60 kilometres down to the surface. And just from the geometry of the satellites, that can mean that the tangent points can drift in the horizontal by a few hundred kilometres. So it's always worth bearing in mind when we start quoting what the good vertical resolution is, that we do have a broad horizontal weighting function, and those horizontal shapes, perturbations will bring us into the vertical as well. Now, I'm just going to go through the processing steps as I see them, because I think this kind of informs how we've tried to assimilate the data. This is array optics processing of GPSR observations. There are more complicated processing approaches, but they don't really convey any more physics, but I'll try and give you the key points here. I mean, kind of lesson number 1 that we always try to reinforce is, GPS receivers do not measure temperature, or even ray bending directly. They're a timing measurement, fundamentally. So we look to see, we essentially get a time series of phase delays of the signal going across the curved path between the 2 satellites. And we get those time series of phase delays at 2 frequencies, 2 L-band frequencies. I've got L1 and L2, they can be slightly different frequencies now, but the key point is you get 2 frequencies. These phase delays are calibrated to remove special and general relativistic effects. That's not something I know terribly much about. You can find the information in this paper by George Hodge. And the key point is that here that we measure the time delays with atomic clocks. We then convert these total time delays to what we call the excess phase delays by subtracting the delay we would have expected for the straight line path between the satellites. So then we get these time series of excess phase delays, and then if you take the time derivative of these excess phase delays, we get Doppler shifts associated. So we get a Doppler shift and how that varies with time. The key point being that the 2 satellites are moving. So even if you had a straight line path, you would have had some Doppler shift, but the bending itself changes the Doppler shift that you would get, that you observe because of the angle that you intersect the two satellites. So we get the Doppler shifts, and then we move on to producing bending angles from the Doppler shifts. Now, an important assumption that sometimes is forgotten is that to go from the Doppler shifts, the L1 and L2 Doppler shifts, we have to assume something because it's an ill-posed problem to derive the bending angle. And what we assume is that the parameter, the impact parameter, this nr sine phi here, this is the geometry, the radius here, we assume that this parameter is the same at the two satellites. So it's the same at the LEO and the GPS. And once you make that assumption, and if you know the position and velocity of the satellites, you can derive the bending angle as a function of this parameter, the impact parameter. But it does assume this particular parameter is essentially a constant of motion along the ray path. So at this point, we've gone from phase to Doppler to bending angle for the two frequencies. So we have the L1 and L2 bending angles, and we have to then try and isolate the atmospheric component of the bending. Now, the ionosphere is dispersive, so that means the bending associated with the L1 and the L2 frequencies is different, and it can be shown if you just take a linear combination of the L1 and the L2 bending angles using the frequencies of the two signals, you can essentially correct out the ionospheric bending to leave you with the neutral bending angle, the ionospheric corrected bending angle. And there's a lot of work in terms of the climate as to climate research as to how good this ionospheric correction is. Are residual errors varying with time? And I think the latest results suggest that it does vary with time, depending on where you are in the solar cycle. But it's more important for retrieved temperatures using the standard GPS retrievals than it is for us using NWP, providing that we're assimilating the data with realistic observation error statistics. Just to give you some idea of the magnitude, this is a simulation exercise where I've plotted here on this axis here is the height of the bending angle above the surface, effectively. This is the L2 bending angle and the L1 bending angle, and this is the corrected bending angle here. This is a logarithmic scale. And I've also superimposed the observation error that I assume essentially above 30 kilometers, which is 3 microradians. And the point I want to make there is that the neutral bending angle soon approaches, well, firstly, the correction that you do, this is a solar max example, is a very important, it's a very significant contribution to the overall uncertainty and bending angle noise, and the magnitude of the bending angle, say at 60 kilometers, is very close to the observation error that I use when I simulate the data. So we don't expect to see much information pretty much above 45 kilometers when we simulate the data. Now, once we've gone through that, and we have our ionospheric corrected bending angle as a function of impact height, there's a very neat mathematical transform that I certainly didn't know anything about before I started this particular subject, where if you assume spherical symmetry, you can relate the refractive index as a function of a height variable to the bending angle profile. So the bending angle as a function of impact parameter can go through an Abel transform to give you a refractivity as a function of height, and the inverse is you can write the bending angle itself as a function of the gradient, the vertical gradient refractive index with respect to this coordinate, which is it's just a convenient coordinate we use, which is the product of the refractive index times the radius at a point on the ray path. So you have this very, very neat Abel transform pair that has been kind of the foundation of a lot of the simulation approaches that we've tried so far. Just a bit of terminology here. I will interchangeably talk about refractive index, which is small n, and refractivity, which is a more convenient variable, which is big N, which is 10 to the minus 6. So the refractive index is 1 plus 10 to the minus 6 times the refractivity, where the refractivity you can then relate to pressure, temperature, and water vapor pressure, and 2 empirical constants that I'll say a bit more about later. just a reminder of the key steps. As I've said, we have excess phase that we go through. We go into Doppler shifts, and then we assume spherical symmetry to get bending angles. We do the ionospheric correction. And this, generally speaking, is where we assimilate the data now. We assimilate the ionospherically corrected bending angles. In the early days of cosmic, some people assimilated refractivity, like Metalvis, Environment and NCEP, but generally speaking, we've all moved to ionospheric corrected bending angles. And nobody would try and assimilate potential retrievals that I'm not going into here, but that was dismissed a long time ago. I think what the points I would like to make is, here, before we get started, is why are GPSRO observations useful in NWP, particularly given that we've already got millions of radiances. And I would emphasise the complementary nature of the RO to the radiance data. And to me, the key characteristics are that the RO can be assimilated without bias correction. I tend not to say RO is not biased, because, as we know, forward models and observation processing can introduce bias. But we've all demonstrated in our systems that we can assimilate the data without bias correction. And that means that RO is a very important anchor measurement to the bias correction schemes of radiances. And this obviously has relevance to climate reanalysis as well, as I'll show later. And also we have the sharp vertical weighting functions. That means that we can see structure with the RO that's very difficult to see with the radiances. So some structure, sharp structure that would be in the null space of the satellite radiances can easily be viewed, observed and corrected in bending angle space. And so I think that's why RO has had an impact. I'm not one of these people that thinks that all we need is RO. I think we need a balanced observing system, and I'm trying to point out here why RO has a role in the global observing system. Let's move on. Just an example of the sharp vertical weighting functions. So this just shows the sensitivity of a simulated bending angle, which has a tangent point around here, and you tend to get a very, very sharp structure around the tangent point that goes from negative to positive, and I won't go through this now, but you can relate that to the fact that the density is 1 over temperature, and the derivative is related to the upper level refractivity and lower. You get this very sharp structure around the tangent point. You get this lower hydrostatic tail here, which is related to the need to convert the model levels to geopotential height levels, so that's an important step. And also it means that you, in principle, you derive surface pressure information from occultation, but I won't go into that in much detail here. The key point here is when you compare this weighting function to radiances, it's going to tell you something different to the radiances that you already have in the system. I'll move on to what we do, how we simulated the data initially. So we did what was called the geometrical optics approach, and that just essentially means we integrated this integral that I introduced earlier, the bending angle as a function of impact parameter, which is related to the vertical gradients of the refractive index multiplied by this strange looking factor. We initially ignored the real two-dimensional nature of the observation, because we know it has a two-dimensional nature, but we just assumed that we could treat the data as a vertical profile type observation at a signal point, so we didn't include a tangent point drift. The integral here required just a few simple steps. We have to evaluate the model, the geopotential heights of the model levels. We do have to do a transform of geopotential height to geometric height, and also radius value, but that's quite straightforward. We need to know what's called the radius of curvature in the location of the observation. We then calculate the refractivity, as I was saying earlier, from the model P, T, and Q, model level P, T, and Q. And at the time, we were using what was called the Smith and Weintraub refractivity constants, which were from a paper in 1953, so it's hardly modern science. And when you actually read the paper, you realise that paper is a review of earlier results, and it's from 1950s observations of these coefficients. And then once we've got the refractivity, we then assume that it varied exponentially between the model levels. And the nice thing about that assumption is that it drops, the integral can be solved analytically, and so if you look at the bending angle contribution between two model levels, it can be written in terms of the Gaussian error function. This is related to the change in refractivity across the model level, and this would be the refractivity on the lowest model level. So you just end up, if you want to know the total bending angle, so this would be between the ith and I+1th model level height. Obviously, to get the total bending angle, you just sum up those contributions. One nice feature is that the way we did it is that we handled the extrapolation of the atmosphere above the model top quite easily. If you assume that the refractivity decays exponentially above the model top, which I think is an assumption that most people make, essentially all you need to do is set this error function to 1 when I+1 is the lowest model level. So then you don't have to do lots of extrapolation model levels and numerical computations, you just compute the error function. And the error function itself is not a particularly difficult thing to compute. We just use a simple cubic polynomial times an exponential. So there was talk about this being a very slow way of solving the problem at one point, but that's just not correct. You can compute these things very quickly.
You need to click again.
Oh, sorry.
DJ joined the meeting.
Okay, sorry. What I would say is, despite the simplicity of the operator that we put in on day one, it did have an immediate impact, and this is quite a striking result. We put the RO data, the cosmic RO data in on December the 12th, 2006, and what this shows is the short-range forecast and analysis departures with respect to radiosonde temperatures in the southern hemisphere at 100 hectopascal, and also for the geopotential heights. So these solid lines are the A-B standard deviations of the forecast, the analysis, and these are the biases of the background and the analysis, and these equivalent for the geopotential heights. And what you can see there is we'd had a long-term bias on these levels. So our short-range forecast would be biased against radiosondes, but as soon as we put the RO in, it kind of pinned these biases down and brought the short-range forecast into much better agreement with the radiosonde. So that was probably the most striking result that we got as a result of the RO going in. And there was no other change that could account for this particular improvement. Now, since that time, I won't go into all of these in great detail. I just want to mark some useful papers that are worth looking at. Some important changes that we did introduce, some really quite surprising results from Environment Canada, where they showed that actually you should really take into account the impact of non-ideal gas effects when you're doing both your computing the refractivity and your computation of the geopotential heights when you're simulating RO data. That was work by Joseph Aparicio. That's informed some of our changes. And also there was a flurry of papers basically on the refractivity coefficients themselves. Some work was done here by Lydia Kukarol. I tried some work, and also Joseph at Environment Canada. You don't need to know the details here, but one remark that's probably worth bearing in mind is all three centres now use slightly different refractivity coefficients, which is not an ideal situation. But I don't think it's a major issue, but some kind of work on why we're doing that in the future, and maybe coming up with a best set of coefficients is something we should look at. Another thing that we put into our system that you guys put in before us was tangent point drift. As I said, when we went in day one, we just assumed that the tangent point did not change with time. We just took a representative point. But I was asked to reassess this essentially as a result of discussions with Mike Rennie and John Eyre, who were at the Metaphysics at the time. And that was stimulated by some work that was done at the University of Graz. As I said, Métier de France and NCEP, you already included this in 2007, and Lydia published the specific impact a bit later. And it was an area that I certainly didn't think was an important source of forward model error, because we were already doing a very good job in the stratosphere, but that was incorrect. It was very clear that it was a good change. I'll show you the impact on the statistics. I'll just show you here. Click. Goodness me, can't keep up. So this this shows you the bending angle statistics before and after I put in the tangent point drift. This is for our Cosmic 4 satellite departure statistics, and this is for the GRASS satellite departure statistics. One thing I do, I tend to show my statistics of observed minus background divided by the assumed observation error, assumed bending angle observation error. And certainly for the cosmic simulations, it was immediately apparent that this was a very good change in terms of introducing the tangent point drift. So that was one thing that he certainly did better than us on day one, and it was a good change that we were pleased to make. It made less impact on the GRASS departures, and mainly because the GRASS departures were defined in terms of, you get what's called an occultation point, just one lap long for the occultation point. And the cosmic tended to give you an occultation point which was referencing the lower troposphere, whereas the GRASS was giving you an occultation point which was more relevant to the mid-stratosphere. So that's why the impact was not the same in the two systems. But as I said, that was a really good change that we adopted from you guys. More recently, work that Chris Burrows noticed. He noticed when he plotted the bending angle biases using our operator, and he superimposed the model level heights on the biases, he could see a very distinct structure between the model levels. So this was the Metavis model levels. These are the bending angle biases, the solid line in the Metavis system, and you can see this very distinct pattern here. This larger bias is nothing to do with the RO. That is a model, an NCEP model bias or forecast bias. These are the standard deviations over here. So we set about trying to work out what was going on here, and it turned out to be related to the assumption of exponential decay across the model levels. It was starting to fall over when the model level separation was very large. So we were able to come up with a slightly improved mathematical solution. So we essentially allowed, what I had was a k value in the integral earlier on. We allowed that k to vary linearly within the model levels, and we were able to reduce the structured bias. Didn't completely eliminate it, but we improved it quite considerably since that point. So the solution then of our bending angle integral is an error function times some of the functions, but it's still relatively straightforward to compute. But the big probably change we've made over the last few years is to move to the 2D operators. Now, the 2D operator is trying to take into account the real two-dimensional slicing nature of the limb observation. As you'll be aware, when we're doing a 2D operator, we're trying to minimize the forward model error, which is the operator acting on the true state minus the true noise-free observation. And when you're trying to build these operators with a lot more physics, there's always this kind of trade-off. You want to go with, what extra information do you think you're going to squeeze out of the observation versus what are the additional computing costs. I'll be completely honest with you, I don't think this particular change has had a big impact in terms of forecast scores, but it has had an impact in terms of our ability to fit the observations. So we have improved fit to observations. So I'll just show you. This is just the central geometry. Previously, for a bending angle, we would just compute an integral at this point here. But for the 2D operator, we have to know where we are within the two-dimensional plane. And the way we did it was to essentially provide 31 profiles in the slice to our observation operator to allow us to compute the bending along this 2D grade path. So you'd have to be able to interpolate the 2D information to a point on the grade path. The numerics is not that difficult to do. The only complication is really when you're trying to do the tangent linear adjoints. The adjoints in particular are a mess. When we put this in, we defined the 2D plane in terms of 31 slices, 31 profiles separated by about 40 kilometres, covering about 1,200 kilometres in the horizontal. We did make some changes to the tangent point drift that I can talk to you later if you're interested. Plus, we don't actually use 31 profiles in a uniloop of the 4D bar. We actually use, I think, 7. I'd have to check that. Because taking into account the inner loop is a lower resolution than the outer loop. We don't need as many profiles. And that saved the computing costs quite a lot. So this is not seen as a particularly costly exercise in the European Centre at the moment. Just, you probably don't need to go through this. As opposed to solving this integral, I've got to just solve this set of differential equations defining the rate path through the 2D slice. And I just took the information from Clive Rogers' book for this particular solution. Just to show what it did to the observation statistics, so this is the change in the fit to the observation. So if you look down here, this is percentage improvement of the standard deviation. So around about 4 or 5% in the troposphere. I don't quite know what this particular kink is here, this one particular example. But generally speaking, we improved our fit to the observations over the entire vertical column. So it was seen as good change. We take a view as we put more physics in, we'd expect to see a better fit to the observations. We did. The forecast scores weren't particularly spectacular, but nevertheless it was a physically justified change that didn't come at a particularly high cost. One area that I am currently working on is looking at the continuity of the refractivity gradients in the vertical. The operators in the ROMSAP codes are never worried about this. I've never enforced continuous refractivity gradients across the model levels. Whereas I know NCEP, I think you do that. So I revisited this area because of recent work by Shay Gilpin and Micanthus at UCAR. So what I've done in the 2D operator is fit cubic splines to the log of refractivity and then computed the bending angles. And actually that does look to be a physically good change. And I'll show you why I think that. This plot here is showing the variability of the simulated bending angles divided by the mean of the simulated bending angles for my current 2D operator that's in operations and my spline 2D operator. And what I've superimposed then is roughly where the ECMWF model heights are. And you can see that I'm not getting the variability between the model levels that I should be getting as a result of the current operational implementation. So I think the spline step is a good idea to introduce. The only slight problem is that because it's always on this side, it tends to increase the underlying speeds. So I'm going to have to explain that as to why this is a good change in the future, because it degrades the fit to observations. But there's no physical reason why we would expect departures to look like that. Sorry, simulated bending angle statistics to look like that in vertical. So that's where we pretty much are. We're trying to improve the operator all the time, and that's what's being tested at the moment. I should say, before we get on to the rest, this is a global error model that I assume when I assimilate the data. I currently ignore vertical error correlations, bending angle correlations, which are certainly not zero, but it's difficult to put in vertical error correlations in something with tangent point drift, because you end up having to put in horizontal observation error correlations at the same time. The bending angle uncertainty, I assume, is 20% at the surface, falling to 1.25% at 10 kilometres, and it stays at that level until that reaches 3 micrograms. And if you look at percentage space, that just starts to increase. This is a global model. I use it for everywhere on the Earth, and I also use it for all satellites. I don't use any inflation between model levels, which I think is something that you guys do. I am not claiming this is the last word, and I certainly look to improve it in the future. But I would say it's not far off. It's not wrong by factor of 2 to 5 or anything like that. Well, I say that maybe it's a bit too conservative in home regions, this round here. But it's our working system currently. But it's an area that I will look at in the future.
So would you expect vertical error correlations?
Would I expect?
Because.
Yeah. The reason you get the vertical error correlations is because of the way you take the derivatives, and in the processing they will smooth the data and take the derivative at the same time. So you end up with correlations that look like a sinc function, essentially. And when you do the kind of de Rosier type things, you get correlations that look like that. problem I've had in the past when I've tried to put correlations in, before I put change point drift, is when I put correlations in, it tried to increase the size of increments. And I couldn't understand why at the time, so I abandoned that. But more fundamentally now, vertical correlations with tangent point drift means you have to deal with horizontal correlations at the same time, which is an interesting line. Okay. So, what do we have? What are we using currently? As you'll all know, Cosmic was the big change that we had in 2006. It is still going. Sporadically, we get Cosmic 1 and 6, and we get both up to 350 prevars per day. If they make it to December this year, that will mean that they'll provide data for 12 years, which is not bad for a 5-year mission. That was an operational demonstration mission. But more likely, when we just get Cosmic 2, we're only getting 250. The bulk of the data we currently get, and I have to say this because I am funded by EMC, is METOP grass data. So don't forget the EMC contribution to RO currently. That's over half the data we get. We also take some data from TerraSAR-X and TandemX, which are research missions. It's not their primary mission to provide RO, so we're relying on goodwill to some extent. And recently, I know this is data that you can't use, we've started using FYC GNOS data down to about 10 kilometres above the surface. We don't assimilate it all the way down to the surface. But it's not quite as good quality as the METOP data or the Cosmic data, but it's not far off, and it's worth putting in, particularly given their very ambitious plans for more RO data.
Can you say something, what's the fundamental difference between them? All of them? Quite
often it's just the instrument's ability to track the signal as you get down into the low troposphere. So, for instance, as you go into the troposphere, you get what's called atmospheric defocusing. The bending always leads to a loss of signal to noise. The amplitude will always reduce. And as you hit the low troposphere, in particular with sharp gradients, you can see these really big fluctuations of the amplitude, the energy that is riding the signal. And it's your instrument's ability to capture the signal during that. And in particular, when you've got rising occultations, when you're actually starting in from a situation where you get a very little signal, you get these big fluctuations, and to actually get an occultation and to get bending angles through that period is very difficult, so you need a good receiver and good tracking loops. I'm not the best person to talk about that stuff, but that's my understanding. So, I'll just briefly show some very recent experiments that were performed by Niels Bohrmann's groups. And these are denial experiments, so relative to a control where everything was in, and what he took out was all the microwave radiances, all the infrared data, all the RO or AMVs, and all conventional data. Quite two extended periods, pretty good horizontal resolution, up to 80 kilometers. Caveats: we have this on some of the data river simulations. He didn't rerun that. I don't think it's a big limitation, and it's not a coupled system. But one thing I do want to point out is that if you look at the number of data that are assimilated in our system and how it breaks down, you look at the microwave radiances and the IR radiances, the number of RO data, I'm getting my excuses in early here, are not a lot. This is about 2% of the data that we assimilate. You could plot it out as the number of instruments that you assimilate, which I don't think is particularly fair on the RO, because it looks as though we've got an eighth of the data, which is not true. This is the number. Bending angles that go into the system represent about 2% of the data that's assimilated in our system currently. So it's doing a job on top of a lot of radiance data and a lot of conventional data. What I'll show is I'll show fits to conventional observations in short range, i.e. 12 hours. In the medium range, I will show some verification against operational analyses. Some people would disagree with that approach. They should say own analyses, but I'm going to just show you operational. How do the forecast, so I'm looking at how the forecast error statistics worsen as a system is removed. So if things got bigger, then that means your observing system is doing a good job. So a positive number implies a positive impact from RO. This shows the global fit to radiosondes as a result of removing all the different sounder systems. The black line seems to win all the time on every plot I'm showing, but this is the microwave sounders denial. So when you remove them, you can see a pretty solid impact all the way through the atmospheric column. The RO impact here, so this is how the fit to radiosondes worsens when RO is removed from the system. You can see a pretty solid signal from 300 hectopascals and above in terms of the temperature space. If I specifically looked at southern hemispheres, it's a big impact. It's almost 7 or 8%, but this is globally averaged here. You can also see that the infrared radiances don't have such a big impact in terms of the radiosonde scores here. So these are the fits to the short range forecast fit to the observations. This is the analysis fit to the observations. This is the more important one, I think, in most things. So this is really in line with kind of what we think the information content of RO is in terms of the temperature space that we expect. We didn't expect it to produce a lot of temperature information lower down. In fact, we would expect it to produce more humidity information as we move lower down. But I'll show you that's not entirely the case. This is the humidity information, again globally average in terms of the fit to radiosondes feature on this. This is the microwave radiances having a big impact. Clearly, the high-res infrared are having a much bigger impact, and we are not currently getting a lot of impact on tropospheric humidity from RO, and that's a question that we have to consider whether there's just not enough RO in the data system to really see an impact. I don't know, but that's where we stand at the moment. One interesting result that you may have an opinion on that I'm still scratching my head about because as Andrew said, my background is physics rather than meteorology, is I am a bit surprised that RO and also the microwave data is having an impact on stratospheric winds in the tropics, because there's no obvious balance that we have in our system. So the assimilation of mass measurements in the tropics is actually improving the winds in the tropics. And one of my colleagues has shown that the assimilation of wind measurements is improving the fit to the mass measurements as well. So the NWP system knows what it's doing, but I'm still working on precisely why RO is improving the winds in the tropics. But it's an interesting question. Just to show you the medium range scores, these are quite difficult to see. These are the southern hemisphere scores on various levels, 1,000 hectopascals up to 100 hectopascals here. So this is the northern hemisphere and the tropics. And what we're looking at here is how the standard deviation of the forecast error has gone up. And we're looking at the forecast times here. There you go. Now these are verified against operational analyses, and that's what some people would dispute. They will dispute the magnitude of this big increase around here. But what you can see is that RO is doing pretty well at 100 hectopascals in the tropics, pretty well in the southern hemisphere, less well in terms of the northern hemisphere scores. You can't see the green line in the medium range, but if you look in the tropics and some stratosphere, where we're towards day 3, 4, 5 in terms of statistically significant impact, which is reasonably encouraging given the numbers we're going. So that's where we are at the moment. I think the point I would make is that we are seeing a clear impact in terms of radiosondes, temperatures, not much in terms of tropospheric humidity at the moment. Medium range scores, not as large as other observing systems, particularly the microwave sounders. But bear in mind the cosmic numbers fall. The RO numbers haven't fallen dramatically because of the other RO instruments. But the number of radiances has increased a lot over the years. And I think, given that we've only got 2% of the data going in, we're not doing a bad job. Nevertheless, we're trying to kind of move towards an order of magnitude increase of the RO observations to say at least 20,000 profiles per day, based on various losses and so on. Now, I just want to go briefly through this. Sorry, I've taken a bit of time. I suppose I was a bit late. I just want to show some results from Adrian Simmons, which I think kind of really show the importance of RO as an essential measurement for reanalyses, and the point that the consistency of some of the stratospheric reanalyses improved since 2006 as a result of cosmic going into the system. And this is a nice plot that Adrian produced me. So this is the mirror, this is the tropical mean 100 hectopascal temperature, so it's a 12-month average, 100 hectopascal temperature from MERA and era interim, and there was clearly a bias between the two, and there was a feeling that we had a cold bias for a period that compared to MERA. Now then JRA, now the point here is that era interim assimilated the RO, but MERA didn't. JRA 55 became available, which assimilated the RO with a different approach, but assimilated the RO. That came in, and it aligned up quite nicely with era interim. Then MERA 2 came along, which assimilated the RO data, and you can see the MERA 2 with the light blue line. So it's a bit difficult to see, but essentially all of these have come together in much better consistency than before. And the red line is the new era 5 system as well. This has probably been filled in now. So if you compare the kind of pre-2006 to consistency in terms of these temperatures with post-2006, there's clearly been a big improvement. And I would argue that is primarily as a result of assimilating RO as the anchor measurements. And the nice thing about that is these are different assimilation approaches that have been done at JRA 55, ECMWF, and also here. Just a few, quickly, I'll go through some plots that show something that's interesting that's not as obvious to people as you might think. I did some low resolution reanalysis experiments with RO in and out, where my control experiment's got everything and RO's assimilated and so on, and no RO as you'd expect. Then we do a reference where we take out all radiance measurements and all aircraft measurements, but we keep RO in the system. And then we do a reference, we put AMSA 14 back in. Now what I want to show is that the impact of the radiances on the mean states of the reanalysis. Now this is the difference between the control, which has got all the radiances, and the ref, where the radiances are missing. And it turns out that this big pattern up here is mainly due to AMSA channel 14, which is assimilated without bias correction. So it is also treated as an anchor measurement.
What's the scale of that?
So this is going, sorry, it's come out very badly. This is going up to minus 10 Kelvin. Okay, so this is, so let me see, this probably comes out here. This line here is minus 4 here, and this goes minus 6, and it goes up to minus 10. So I'll show you in the next plot. So the interesting thing here is that we've got this huge bias over the pole, and RO's in the system. And the question is, well, why RO's in there, it's assimilated without bias correction, why on earth is it not seeing anything here? And if you look at if you just plot out this bias, averaged as profile, this is better now. So you see this is minus 8 Kelvin here. This is the temperature difference between, this has got the AMSA back in and minus ref, but the point is still the same. So you've got this really huge bias that's increasing with height, and RO is just not dealing with it at all. And the reason, so this is the bending angle differences for those two cases in the same region. And you can see a minor change in the biases of the RO at 40 kilometres, but nothing particularly significant. This is 0.06 here, and this is 0.06 of the assumed observation error. This is tiny. This is the difference in the standard deviations. Not a lot to be seen there, despite the fact you have this huge temperature bias. And the point I want to make here is that RO struggles to see temperature biases like this, because these biases can produce virtually no difference to the refractive index. There's a compensating factor where you move the heights of the model levels up, but the refractivity on the model level has changed. As a result, if you look at the refractivity as a function of height, it doesn't change at all. So this is what I call the RO null space, and you should always be aware of. So RO is great at correcting biases that have got short scale structure. It struggles more with this kind of
Right. So we get that way we get very good resolution near the tangent point.
Yeah.
The resolution decreases in the limbs.
Yeah.
And we probably want to change that a little bit, because I think we feel that in the limbs we don't need that high the high resolution that this S variable gives us.
Okay.
So the plan I'm talking to Lydia occasionally about this,
Yeah.
is to use the existing S variable near the tangent point, but have it blended towards the model levels at elevation where
Yeah.
where you're in the sort of limbs of the Gaussian type influence.
Yeah, I talked with Lydia last week, so we will follow up. So because I'm implementing the SI operator into Jedi,
Okay.
so I work with her and then work with you as well. So I think that part probably we can.
Yeah, I
talk
think
a
it's,
little bit
it's,
more about
it's
that.
good. I mean, I think,
Mhm.
you know, as I've tried to say, I mean, we don't have all the good ideas at ECMWF.
Mhm.
If there's a good idea elsewhere, we try and we take on best practice. And,
Sure.
I think the operator we did was pretty good and it's quite efficient. But the use of the spline has given me a slightly different perspective, or maybe that's something we should look at putting in the future. There's continuity of gradients. Some people always got very hung up on, but I learned Snell's law with a discontinuous, glass air. You don't have to have continuous gradients for these things. But yeah. I think if anything comes out of this that we can collaborate more on forward model development, that would be great.
Yeah.
Because the SAF would like that.
Mhm.
Yeah.
You were saying that you don't have much of a tropospheric water vapor signal.
Yeah.
When we did Merit 2, one crazy result we kind of had was we were getting pretty substantial stratospheric water vapor increments. It was through no good physical meaning. It was just our background errors were kind of inflated.
Oh, okay.
And it was kind of the path of least resistance to
Okay.
Dom's signal.
Okay.
I'm curious if you guys have looked at your stratospheric water vapor increments at all.
I took it out.
Okay.
This talk to get. We get there's this spark reanalysis comparison papers.
Right.
If you look at there and you look at the stratospheric water phase paper, there is a discontinuity at the end of 2006, and we don't increment the humidity directly.
Okay.
But the argument being that because we were improving the tropical pools, we were reducing a bias of the tropopause temperatures. We were getting moisture air. It wasn't, the freeze drying was at a warmer level, so we've got more humidity in the stratosphere as a result of RO being in the system. But that's not a direct increment on the humidity. That's a dynamic or response to the RO. So we see something, and it's there in the papers as well.
Yeah.
Yeah, I can show you the plot if you yeah.
Do you have any plans to move towards a more fundamental operator based on the phase delay itself? This is something that Andrew's mentioned a few minutes ago. Or a hybrid system where you use the bending angles of first stress and then refine that using phase delay.
It's interesting because the phase delay kind of assumes that you probably wasn't clear about this. I don't try and hit the satellites with my operator. I just compute the bending along the path. And if you start doing phase delay between satellites, you have to remember that in reality you've got the ionosphere there as well. So the neutral path itself won't fit the satellites. You'd have to model the ionosphere to some extent to do a phase delay operator and get the curve between the satellites. So I've got no immediate plans. But if somebody gives me 3 years to think about it, then I'll have a go.
And eventually we're going to have to model the ionosphere as well, right?
Well, we do have a 1D operator which has got like a Chapman layer on top of it, which in principle you retrieve the Chapman layer parameters. That's the standard equivalent of an exponential decay atmosphere. So you retrieve 3 parameters from the L1 and L2 bending angles by simulating them directly as well. So yeah, we have that capability in the ROMSAF SOAP code. So if you're interested in that, how we've done it, that's there. But there's no immediate work within the centre to put an ionosphere on top, as far as I'm aware.
In the history of retrievals or assimilation of satellite data, we always seem to get a benefit when we go to more fundamental
Yes.
forward operators.
Yeah. I think, yeah. It may come to pass. It's not obvious to me that it's. I think we can improve what we've got at the moment, but maybe we need some some young postdocs to start working on this.
The other thing is, now they're thinking of putting up these little CubeSats, which
Yes.
I think at much lower orbits. So presumably the Fresnel dispersion of the ray will give you a better resolution for those operators. Is it time perhaps to deal explicitly with the effective beam width of these rays?
I'm not sure. I don't know how I'd answer that question. I'd have to check to see. I know they have slightly lower altitudes, but I don't.
Some of them are like 380 kilometers.
400.
Yeah.
So you're in the middle of the ionosphere, but I mean, I don't think it would fundamentally change the way I would assimilate the data. But I'd have to think about it.
I mean, you'd expect them from Fresnel theory to give much sharper,
Yes.
narrower beams.
But then, yeah, they in principle give sharp and vertical, but you've always got this horizontal averaging that you have to consider as well, which would tend to smooth things over. But I don't know the numbers on that. I've not actually thought about that. Yeah.
Have you guys, because you made the point about ops counts, right, and they've been dropping precipitously, have you seen any signals reflecting that you expect some sort of another transition with Cosmic 2, for example, or do you think that the systems themselves have just kind of stabilized in a sense that...
The Cosmic 2 ops count have declined obviously a lot in recent years, but the UMETSAT counts have gone up and we made better use of that. So overall, we're going with about 2,000 profiles per day, which is a little bit lower than maybe Cosmic 2 peak, but it's not so different. But at the same time, the number of radiances that have gone into the system, the other observations, as you know, you've got now 2 ERZs, Chris airs, whereas when Ara went in, you just had the airs, for instance. So if you look at these FSO plots, and you look at the time series of those as what percentage RO is contributing, it's kind of halved over the last 10 years,
right.
I think. So we see it in that plot, but whether that's, some people take that with a pinch of salt.
Sure.
Another thing I noted in your talk, you discussed the rays going right down to the surface in some cases, but the assumptions I always had was that you get all kinds of problems with super refraction layers when you get close to the oceanic surface in most of, at least the tropical ocean.
That was a level of detail that I decided not to put into the talk, but yeah, you can't go below a ducting layer.
So you
can't go below a ducting layer. You can't compute bending angles below a ducting layer.
the rays, there's a gap, but there's a possibility that you can get a ray or two that goes penetrating through the super refraction layer.
The problem with once you have those ducting layers is you end up with an extremely sharp transition of your bending angle going like this, it goes like that, almost. And the problem there is, if you look at them, the gradients of bending angle with respect to humidity in those cases is huge, and you can't use that in the inner loop. And we're better off bailing out than trying to use those data at the moment.
Lydia and I were thinking of at least trying to get some information below the super refraction layers if possible, but we do realise that you're in a very humid environment there.
Yes. No, I think, I think it's, as soon as the bending angle looks as though it's almost horizontal, you're going to have trouble in the minimisation, I think.
Yeah, are you thinking about ground-based receivers? And is that what you were thinking about?
No, these are occultations.
It's just for occultations.
Yeah. I trimmed some stuff out, and maybe we can talk about that later. We don't. Once you hit one of those ducting layers, that this quantity x equals nr actually no longer is single valued. It starts to go back up. Right? Yeah. So you have this region where it kind of goes all over the place, and that you look at the bending angle as a function of impact roses. If it should have a singularity, according to that. Now, in reality, the wave optics won't give you a singularity and so on, but it's just incredibly hard to know how to model that.
No, that's one reason why we're moving towards a geometrical radius vertical coordinate instead of using the refractivity radius as a vertical coordinate
Right.
in these calculations.
Yeah.
But
Okay.
that should also help us to get closer to the
Yeah.
dangerous super refraction.
I think you'll run into trouble with bending angle profiles that look anything like that.
Yeah, but you're probably right. But,
In fact, I
relatively
mean-
large observation errors.
In fact, I know that the Metafis had a operational minimisation problem because they didn't have a catch, a check for that at one time. Where they didn't get convergence on the 45 because of one of those kind of problems. Now that was with our operator. Maybe that you can do something clever, but I think if you're going to be conservative and careful, you bail on those bending angles rather than try and squeeze them out. That's the way I think look at it at the moment.
Well, we'll go cautiously on that.
Yeah, well, I mean, if you get it working, then
Yeah, I think
we'll take it on board and
one
put it in.
of the problems is that these tropical boundary layers are not that deep anyway, a kilometre or so. So
It's-
you're not going to get many rays that will fit in
It's
below
those
that.
kind of regions, the kind of semi-permanent stratocumulus regions.
Yeah,
They're really difficult. They're really difficult, and you make a very small change to the humidity there, and you get a huge change in bending angle. So you put that into your minimisation algorithm.
well, I'd say that's a very useful observation if you can use it though. Get a very precise measure of the humidity.
Well, yeah, if you can. I agree with you, if you can
I'm
use it.
looking on the bright side.
No, well, I hope I'm not. I'm just giving you my experience of, I think there's always a balance of trying. You have to be a bit careful that you're not wandering into a region where the minimisation is going to struggle. And I certainly think with a linear assumption in a loop, those kind of huge bending angle gradients with respect to humidity are problematic.
Of course, using our S variable sort of unfolds the singularity in the arbor transform. So
Yeah, I've never really. I mean, we can talk about this later. The singularity in the angle transform is the fundamental. Are you talking about the in the original?
you got the square root singularity. One of the square root singularity.
I know. I've had interesting discussions about this. You do this thing here.
Yes.
There's nothing fundamental about that. You can get rid of it by a simple change of variables.
Which is what we do.
Yeah, which is what we do. So that, it looks horrible, but it's not a problem. The singularity with respect to super refracting is a different thing. That's a difficult thing to do.
Well, it's a fundamental physical singularity.
Yeah. So that's, for instance, I would just assume that that's x minus a, x plus a, it's 2a. So I've got the square root of x minus a effectively. Or you can do a Koch substitution. That's what we did early on. So that goes away. So, that is not that looks horrible, but it's not. It's easy. The super refraction is more difficult.
Are there any questions on the phone? Okay, I think this discussion's going to go on for a while, but I think we should at least formally close the presentation, and we'll show your appreciation to Sean one more time. I really enjoyed that.